Here we're going to solve a system of equations where you have three unknowns, but only two equations. One way we can visualize this or think of this is that each linear equation represents a plane in 3 dimensions, and when they intersect at a line. So there's not one point that's a solution. Our solution is going to be a line. So there's an infinite number of solutions. And this is called a dependent system. So to solve this, we are going to use Gaussian elimination. And to do that, we first begin by constructing an augmented matrix, which consists of the coefficient matrix followed by the load vector. And so you just more or less pick up all these numbers there. And so just put those numbers there that we see, and really just they're all sitting there, but we don't write the x, y, and z. We just put the coefficients. And already what we have is I had set it up so that in the first row on the top left is a 1, which is what you want anyway. So we don't have to do anything to that. But what we want below that lead 1 is a 0. And so what I'm going to do is I'm going to multiply the first row by 2 and then add it to the second row and put that in the second row position. And so that's pretty straightforward. So there's not really, this is sort of a really rather simple problem, in fact, but it shows what I'm trying to show here about a dependent system. So you multiply the first row by 2 and you add it to the second row, and so that leads, if I change colors just to sort of make it easier to see what's happening here. So I multiply 2 times 1 and add it to 2, and I get 0 right here. Negative 1 times 2 makes negative 2 plus 1 makes negative 1, and etc. We just keep moving along here. And it's a little bit easy to make mistakes for me, but the more I do this, the better I get at it. So I just tell myself I got to, keep working at it. Okay, so we're moving along here. We want to have a 1 there on that second row on the first entry. And it's negative 1, so that's easy enough to solve. We just go ahead and multiply the second row 2 by negative 1 and put that in the row 2 position. So the first row remains the same. And now we just change the second row by multiplying by negative 1. All right, so this is in reduced row echelon form, which has the characteristic that when you look at the first row, the first non-zero entry is 1, and it's to the left of all the entries in the row. Below that, it's to the left of all the other non-zero entries in the whole matrix. Below that is a 0 or zeros. Then when you go to the second row, the first entry on the left, the first non-zero entry on the left is a 1, and that lies to the right of the lead entry above it. All right, now there's nothing more we can do with this. We don't have another row to work on. So we then now write this as a system. So we're going to have x minus y plus z equals 2. That corresponds to the first row, which is what we started off with anyway. And then y minus 4z equals negative 9. Okay, now what we do for these is if you notice, there's no way to solve for z. So we let z be any number, which I'm going to denote as a parameter t. T is any real number. So we can think of that as a parameter. And so z is t, and then we back solve in the same way we would back solve if we said that z is equal to 1, for example. Then we'd solve for y, plugging in z equals 1. So we back solve, but see, y is not equal to 1. Z is not equal to 1, z equals equal to t. So I write y equals 4z minus 9, and I replace z by t. And then we get y equals 4t minus 9. So that gives us that's what we're going to write down, or what we're going to leave with z or y. And then we go over to x, and we have x minus y plus z equals 2. And I replace y by 4t minus 9, and I replace z by t, and then I go from there. The thing that's a little bit, for me, something I worry about is that I don't see right off how I can check my work. I suppose I could find a way to do that. I suppose what I could do is, if I pick any number for t, say I pick 1. Okay, I'm talking about how I can check my work. Anyway, let me just write down the answer, and then I'm going to show you maybe how we can check our work. But the answer is, the solution is all points of the form 3t minus 7, 4t minus 9t, where t belongs to the set of real numbers. I'm just going to sort of do this shorthand for math. From set notation, we write that in, and r is the real numbers. What I was going to say is that if I did want to check my work, which would require me going to another piece of paper, I might as well just do that. If I wanted to check, and then maybe I'll realize this is wrong, but if I want to check, I could say let t equal 1. If I do that, then x is equal to 3 times 1 minus 7, which is negative 4. Y equals 4 times 1 minus 9. And I just basically picked 1 just out of the air, really. And then put into the original equation. And so I'm going to put this into the original equation, and I'm going to see whether this is correct. It's not a full check, but it's something. It depends how much time you have in your hands. But so if I go back to the original equation, I had x minus y. Well, I have to zoom out. Plus z equals 2. And I have negative 2x plus y plus 2z equals 5. Okay, now suppose I put those numbers in there. I'm going to have negative 4 minus negative 5 plus 1. The question, does this equal to 2? And, oh my gosh, it better, but I see that it does. Oh my, that relieves a little bit of something. Negative 2 times negative 4 plus negative 5 plus 2 times 1. Does that equal 5? Yes. So it checks out. Okay, but that's a little extra. Actually, the truth is I don't do that at all. Like it's the first time I've ever done that. But I do want to know if I got it right without, you can always check on it with a computer or something. But Anyway, make this look a little neater. Looks sort of messy there. Don't want mess. Okay, so the one thing I want to point out is that it maybe isn't clear at all to us right now, but this actually is the equation of a line in space. And when we usually write this line, what we can do is we can break this up as follows. We can write this as, although this maybe is sort of a waste time for people, but anyway, you can write this as -7, -9, comma 0, plus, comma 3t, 4t, t. Okay, that's a point. So this is, what I'm doing now is I'm writing this as a vector. And so you could write this as -7, -9, 0, plus t, 3, 4, 1. And this is actually the vector equation for a line, because the solution set is a line. It's that purple line right here. These planes are not really the graph of the planes I showed here. So, but we're not going to do that until a linear algebra class. So I think I'll just even erase what I just wrote there. But anyway, what I said is true. All right, that ends the video.